Well, this is a lecture on Hell's Canyon and the Ringold Formation. Now, Hell's Canyon you've heard of. I assume it's why you're here. We know where Hell's Canyon is located. It's the Snake River. It makes up the state line between Oregon and Idaho. Great. It's a deep canyon, Hell's Canyon. But I also tonight want to talk about something called the Ringold Formation, which is a bunch of sedimentary rock layers that I was bored to tears by until last year. I had no interest in the Ringold Formation at all. Seemed like a bunch of boring lake beds and that's it. But I now am distinctly curious about what's going on with the Ringold, and especially the researchers who have been working with the Ringold Formation. You're like, well, where is that? Well, it's close to home. The Ringold Formation is in central Washington. And there is a connection between the details in the Ringold Formation, White Bluffs, that's the Ringold Formation, Saddle Mountains, that's the Ringold Formation. There's details that have been locked and hidden in the Ringold Formation that help us better understand Hell's Canyon. And you're like, okay, I guess if that's the plan, but I don't see how those two things go together at all. And that's our hope tonight, is that you'll see the connection before we quit. Now, this is a geology lecture, right? So I've got some basic geology questions about Hell's Canyon. Why is that canyon there? How long has that canyon been there? Why is it so deep? Why aren't all of our river canyons as deep as Hell's Canyon? The room got suddenly very quiet. Everybody's thinking now, and that's what we want. So about a year and a half ago, I started thinking that it would be fun to put a lecture like that together, and I knew very little about Hell's Canyon. And I got to warn you right up front, those basic questions have some answers, but we still don't have all of the answers for those basic questions. So this is one of those that I'll bring you up to speed on where we are in the literature and with the researchers, but there's still work to be done with Hell's Canyon and the Ringold Formation. Okay, so how many been to Hell's Canyon before? Okay, maybe 300 of you or so. Yeah, not everybody, but plenty. You got to burn some calories to get in there, right? You can't just take a Sunday drive through Hell's Canyon. There's no road along the bottom of Hell's Canyon and the Snake River. It's remote. There's no visitor center at the rim with a big parking lot and rangers telling you about the formation of Hell's Canyon. There is with the Grand Canyon, of course. So thankfully, there are still some rugged, remote places left, and many of you go to Hell's Canyon almost as a personal retreat. The cell phone doesn't work at the bottom of Hell's Canyon. You can easily go back decades and get away from it all. Whether you're getting in there by jet boat or whether it's you're coming in from Whitebird, Idaho, and coming in on some Forest Service dusty roads for miles and miles, but you can get to the bottom of Hell's Canyon in a various ways, but you really got to work to get in there. If you get in there, and those of us that have, we love it. And maybe after tonight, you'll be more motivated to go to Hell's Canyon if you haven't been there before. Sounds like a terrible place, by the way, Hell's Canyon. What a terrible name. Why would you go to Hell's Canyon or Death Valley or all these terrible sounding places, you know? But despite the name, it's beautiful, and we have plenty of visuals to share tonight. But how can I get you more interested in Hell's Canyon and the geology of Hell's Canyon? Well, I think many of you know this, but maybe everybody does not. Did you know that Hell's Canyon is deeper than the Grand Canyon? And it's not even close. We have a river canyon here in the Pacific Northwest that's 2,000 feet deeper than the Grand Canyon in northern Arizona. So I don't know if you've noticed up here, but I've got a couple of side views of a couple of canyons. Have you figured out what they are? This is the Grand Canyon in Arizona, and this is Hell's Canyon. And generally, the Grand Canyon is about 6,000 feet deep, depends on where you measure, and Hell's Canyon is 8,000 feet deep. Okay, I didn't know that. I can tell my people at the coffee place tomorrow all about Hell's Canyon being deeper. Well, wait, I got something better than that. And this is the observation that got me very fired up about this topic. Not only is Hell's Canyon deeper, it's younger. Those two canyons are not the same age, and the conventional age for Hell's Canyon is half the age of the Grand Canyon. So to review, we have the Snake River digging a hole deeper than the Grand Canyon in half the time it took the Colorado River to carve its canyon. What in the world is going on at that place on the Pacific Northwest map? That's what we're talking about tonight. And you can see, maybe, why it's a work in progress. There's lots of things that would contribute to that successful digging of the Snake River. Okay, but this business about age of a river canyon brings up a painful personal memory, and I'd like to share that with you. I'll make it quick. This is 30 years ago. I'm whitewater rafting in West Virginia, of all places. And you've been whitewater rafting before? It's a fun experience, you know. You've got typically an inflatable raft, and you've got half a dozen people in your boat, and there's kind of a hippie dude, you know, in the back there, your guide, you know, getting you through the rapids, you know, guy or gal. They got the leather bracelets and the puka shells and the hair and everything. They're smart. They know what they're doing. They're kind of chill people. And, you know, they're training you up on how to paddle, and let's do the right side paddle and right side back and all back, you know, and all that kind of stuff. Okay, so we're in West Virginia 30 years ago. I'm fresh out of grad school. I'm feeling pretty good about myself, pretty cocky. And we're on a quiet stretch of the river between rapids. And the guy, you know, strikes up a conversation with the group, and he says, it's kind of ironic, this is the new river, but it's the oldest river in North America. This is the New River Gorge in West Virginia, but it's the oldest river in North America. And of course everybody says, why do they call it the New River if it's the oldest river in North America? And the guy says, I get that question every time, and nobody has an answer. You know, nobody's figured out why it's called the New River. There's ideas, but nobody knows for sure. And then my wife says, well, how do they know it's the oldest river? And he's like, oh, I've never gotten that question before. And my brother-in-law says, well, it's a good thing. We got a geologist in the boat. Nick, why don't you tell this guy? So I'm fresh out of grad school. I'm feeling pretty good about myself. I just start talking. I start lecturing the whole group about the Appalachian Mountains and ages of river canyons. And as I'm talking, this is 1990, as I'm talking, I realize I don't know what the hell I'm talking about. Like it sounded like a pretty basic question. Well, how old is this river canyon, or how old is the river? But I was, you know, I don't know the answer to this question, and I'm still talking to these people in this boat. So at the end of my little lecture, everybody's went like, okay, you know. Everybody knew I was full of shit, right? I didn't know what I was talking about. So I swore from that moment on I would never BS. It's okay to say 3 words, you know. I don't know. You can say those words and still be okay. And we've all been in a room with somebody who's got all the answers. So that was a life lesson for me. But at the time, I didn't know how they figured out how old the New River was, and I've been in geology a long time now, so I have a decent idea. And here's the basic message. You can figure out the age of a river canyon if you leave the canyon. If you're in the canyon, it's very difficult to figure out the age of the canyon, because what are we really saying when we say how old is a river canyon? We're saying how old is the hole, aren't we? That's what we're trying to decide. When did the river start to make the canyon? It's got nothing to do with the age of the rock layers. So let's use the Grand Canyon as an example. These are ages in millions of years for the rock layers exposed in northern Arizona in the Grand Canyon. You with me? The Vishnu Schist is at the Colorado River. It's way down there at the bottom, in the inner gorge of the Grand Canyon. It's 1,700 million years old. It's Precambrian. It's very, very old. Some of the oldest rocks in North America. Okay, old rocks. Does that mean it's an old canyon? Well, I don't know. The guy just said we got to leave the canyon for some reason. I don't even know what he meant by that. That's you talking to your wife now, or vice versa. The youngest, the rim rock in the Grand Canyon is the Kaibab limestone. It's 270 million years old. So if we ask ourselves, how old is this canyon? Basically, when did the Colorado River start to cut into the earth? I think using these ages, all we can say is what? The canyon has to be younger than 270, doesn't it? Let's make sure everybody sees that. Have you ever thought about this? When you're in River Canyon, there's a wall and there's a wall. You got matching river walls, or canyon walls. Have you ever noticed that they match? Like it's sandstone, limestone, sandstone, sandstone, limestone, sand. That's not an accident. Those layers used to be continuous, right? It used to be Illinois. There was no canyon there. It was flat and those layers were intact. And then the river started to cut down. So even 270 million years ago, we had a continuous layer of Kaibab limestone, and all we can say based on these rock layers is the canyon, the Grand Canyon, is younger than 270 million years. Well, that's not a very precise date. Sometime in the last 270 million years, that's not very satisfying. I feel like I need to cut to the chase and do something real. The conventional answer for the age of the Grand Canyon is 6 million years. 6 million years, the Grand Canyon. The Colorado River started to cut into the earth 6 million years ago. It's a young feature compared to the age of the rock layers. Now, the topic tonight is not the Grand Canyon, it's Hell's Canyon. Let's look at those ages. Interestingly, the oldest rocks at the bottom of Hell's Canyon are younger than the youngest rocks of Grand Canyon, right? 270, and here we are 200. Is this the Kaibab limestone? It's not, but it is limestone at the bottom of Hell's Canyon, the Martin Bridge limestone. And there's also some 200 million year old volcanic rocks from the South Pacific. So that's another lecture. We did an exotic terrain lecture last year, which bit off some of that, but we could expand on that at some point. So that's a whole other topic. But the point is, we have 200 million year old limestones and volcanic rocks, exotic terrains that came in from the ocean and docked at that location in the Pacific Northwest, and that rock is 200 million years old. Most of the rest of the walls of Hell's Canyon are 16 million years old. The basalts of eastern Washington are flood basalts. The basalts you see in the Yakima Canyon, in the Columbia River Gorge on the way to Portland, Grand Coulee, etc. So these are kind of familiar rocks to us, and we've already discussed the flood basalts a fair amount. What can we say about the age of Hell's Canyon? Well, it's younger than 16 million, using the same logic we just used. But we have a different answer, a more precise answer. The conventional answer for Hell's Canyon is 3 million years. Remember I said the Snake River has taken half the time to dig a deeper hole. So far what have we said? The age of Hell's Canyon is 3 million years, meaning the Snake River started to carve at that time. Like you got to make the German chocolate cake, and then you take out the knife and you make a wedge and you pull the wedge out and you give it to the birthday girl. It's the wedge being pulled out that's happening very recently compared to when you made the cake. Same idea here. So, 3 million years, that's not a lot of time. And why here? Why was the snake so aggressive just in that spot to dig this deep hole? It's not this deep other places along the snake. Okay. Let's make a quick little list of potential ideas, and this is the loosey-goosey part of the lecture, meaning this is the part that needs more work. But I'm going to throw out a bunch of ideas that have a bit of validity to them, but they need to be fleshed out with more evidence. I'll do it quickly. Is it possible that the rocks at Hell's Canyon are softer than everywhere else? Well, I don't know. Is basalt soft? Well, it is kind of, if you think of basalt in this manner. Many of us know that in eastern Washington, basalt is heavily fractured. There are a lot of vertical fractures, basalt columns. There's a lot of horizontal fractures. I'm fond of saying basalt lavas. Our great flood basalt lavas are pre-cut and ready to be hauled off by a bunch of water. So if that means soft to you, I guess that can work, that we've got a bunch of basalt that might be very easy to erode since it's already cracked up so much. And by the way, are we challenged by the Snake River itself? Snake River starts in Wyoming. It goes Jackson Hole, Idaho Falls, Pocatello, Twin Falls, south of Boise. Here's the snake getting into Hell's Canyon. Here's the snake entering Washington. Lewiston, Idaho, Clarkston, and then Tri-Cities, and then we joined the Columbia. Okay, that's the snake that we're talking about. So why in that one particular stretch we got the floor dropping out and making Hell's Canyon? So soft rock, we get into some basalts, maybe that's part of the story. If we go back a few lectures in this spring series, the supercontinent lecture, do you remember we had Old North America? We had a very sharp boundary where the edge of the basement rock of North America is located. Where was that? Well, we said it was Spokane, and sure enough, that old edge of old North America, and what's on the other side of this line? A bunch of those exotic terrains that came in off of the ocean. Is it a coincidence that this deepest river canyon is basically right on that old boundary? There's a more formal geology name for that section of the old boundary called the WIZ, the Western Idaho Shear Zone. So just think there's a there's a bunch of faults that are shifting a bunch of the bedrock north on the exotic terrain side. It's a shear zone where there's been northward movement. And basically I'm trying to say that there's some big faults in that area. Is there a connection between the WIZ, the Western Idaho Shear Zone, and the location of Hell's Canyon? I'm going quick, and you're like, well, what's the answer? Remember, I told you, all these are potential areas, but we're not going to lock into one of these. I'm going to lean towards one in just a bit. Is this an Ice Age story? Is there a bunch of meltwater coming off of the ice sheet? Well, we're too far south for that. The ice sheet is up here in northern Washington, etc., so that doesn't work. But some of you know there was a big Ice Age flood that came through Hell's Canyon. It's called the Bonneville Flood. The Bonneville Flood. And we have a good date for it. It's an Ice Age flood, not the Missoula. It wasn't Ice Age flood water that came from Montana. It's water that came from Utah, from Lake Bonneville. And there was a hell of a flood that got over Red Rock Pass, dropped into Pocatello, found the Snake River, and followed the Snake. And a major Ice Age flood, one big flood, came through Hell's Canyon 18,000 years ago. 18,000. So a fraction of 1 million years. So to say that Hell's Canyon is 3 million years and then to say this Bonneville flood is why Hell's Canyon is so deep is probably a stretch. In fact, we view Bonneville flood as more of a dumper than a cutter. There's huge piles of Idaho rocks that are sitting in the floor, especially in the floodplains of the Hell's Canyon floor. But it doesn't look like that's a major cutter. Finally, and those that have gone to other lectures know that I'm fond of this, uplift intensifies erosion. It's not that the Grand Canyon and the Colorado River, it's not that the Colorado River is so powerful, it's that northern Arizona is tectonically lifting. And that is an accurate way to view northern Arizona. That this canyon is here because starting 6 million years ago, northern Arizona starts to get a little closer to heaven every year, starts to tectonically uplift, and the Colorado River tries to hold its position. It aggressively cuts. And that's the general view for many of the river canyons in central Washington. The Yakima River south of Ellensburg, Washington, is a river being there first, tectonic uplift due to some folding. That's accurate. But I don't know if we can fall in love with this either, at least in the way that I've discussed uplift in the Pacific Northwest before. I'll do it quickly. Why is there uplift south of town? Right. There's clockwise rotation. The clockwise rotation we talked about last week. The clockwise rotation that keeps coming up in many discussions involving earthquake potential and everything else in the Pacific Northwest. These are arrows. I'm doing it very quickly. Basically, everybody's rotating around Pendleton, Oregon. This is something we've been able to document with instruments, GPS receivers. But northern Washington and British Columbia do not rotate. So we're rotating everybody into a fixed northern Washington, and as a result, we are squeezing we are squeezing central Washington and have been for many millions of years. What's the result? Big earthquakes on the Saddle Mountain Fault, the Menashtash Ridge Fault, the Umtanum Fault, the Toppenish Ridge Fault, the Seattle Fault, as well as forming the ridges that you drive over when you go to Yakima. That's all in response to that crustal rotation. So why aren't I hitting clockwise rotation hard for the formation of Hell's Canyon? Yes. Everybody is rotating around Pendleton, Oregon. Hell's Canyon is to the east of Pendleton. How is this rotation having anything to do with Hell's Canyon development? Now, it's clear we have the Blue Mountains and the Wallowa Mountains and the Seven Devils Mountains on either side of Hell's Canyon, and those have clearly been lifted. But I have not found the right person or the right scientific paper to for sure document why that uplift here is happening. And to me, that's an unsolved part of this story. I can't hold it because the energy is so great right now, so I'm just going to go for it. A pet idea that I have been thinking about, and it's come from a few little stray sentences in papers I've been reading and a few conversations with geologists, is this. Is there a regional tectonic uplift event that we don't know about or don't know very much about? Is it possible that many of the river canyons in the entire Pacific Northwest are energized simultaneously? What I'm saying is, instead of the uplift and the incision of the Snake River being from clockwise rotation, is there something more broad in Pacific Northwest land? About 6 million years ago and about 3 million years ago, coincident with these two numbers. Those numbers keep coming up, and I'll show you some visuals to kind of play with that idea. What I'm trying to say is, it's possible in the next 20 years, we may be able to build a case that the Yakima River and the Wenatchee River and the Palouse River and the Snake River, etc., the Chutes, etc., are all deciding to get aggressive at the same time at 3 million years ago and maybe also 6 million years ago because of an accelerated regional uplift. That's tantalizing for many of us. Nobody's had the ability to kind of put that together in one major message. Okay, I want to do one more thing with the chalkboard, and then we'll go to the visuals. Thank you so much for the energy. Let's erase this, and let's, believe it or not, use the supervolcano discussion we did last week. Like, how in the world would that have anything to do with what we're doing now? Well, the rest of the chalkboard is talking about the evidence we have for this number, 3. Where does that number come from? You just pull that number out of a hat? I said hat. I could, 3, 6, Where does that number come from? I mean, it's just younger than 16, but actually being specific about 3 and 6. What's the story there? Well, I'll make it as quick as I can. Yes, I will. I'll make it as quick as I can. So we know Hell's Canyon is here. And you remember my quick offhanded message that if you really want to figure out the age of a river canyon, you got to get out of the canyon. So if we go downstream of Hell's Canyon, we're suddenly at the Ringold Formation. And if we go upstream of Hell's Canyon, we're in southern Idaho in some lake beds called Lake Idaho. So let's put 2 lakes on this map. Lakes that we know existed. Lake Idaho, Lake Ringold. The Ringold Formation are the deposits at the bottom of Lake Ringold. There's a bunch of beds at the bottom of Lake Idaho. Let's draw those very quickly. There's about 1,000 feet of sedimentary layers making up the Ringold Formation, and we'll just say Lake Idaho. There's a bunch of formal names, but let's not do it. We'll do this, Lake Ringold. Now I got to be careful. Okay, so this is LR, and this is Lake Idaho. And you know what I need to do? I need to get this out of here. Because one of the big messages is when we have these two lakes, there is no Hell's Canyon. There is no Snake River coming through the area. Oh, really? Yes, if we go far back enough in time, we can go earlier than the lavas, we can go earlier than the cutting and realize there was a totally different geography. So these sedimentary beds of the Ringold Formation go roughly between 8 and 3 million years. And the sedimentary beds for Lake Idaho go 8 to 3 million years. I'm going to change this. I'm going to put 2.8 up here at the top. 8 to 2.8, 8 to 2.8, okay? Now, I did a lecture 2 years ago called Ancient Rivers of the Pacific Northwest. Some of you were there for that. And we talked about the Columbia River moving around in response to the great lavas pushing the rivers around. And we used evidence like river cobbles and lava-filled valleys and things like that. Put the lecture out there on YouTube. A lot of people liked it. I got an email from a guy named Jerry Smith. He says, I'm Jerry Smith from University of Michigan. I enjoyed that lecture. But I think you could have used one more line of evidence to prove where rivers used to be. You can use fish fossils. I've spent the last 55 years studying tiny fish fossils in Lake Ringold and Lake Idaho, and I can prove when Hell's Canyon started to form. In other words, when the Snake River used to show up on this map at 3 million years ago. So we'll do it quickly on the chalkboard, and we'll do it again with the visuals. Jerry Smith and others looking at fish fossils in these two sets of lake beds. You've got it now, right? We've got lake here, we've got a lake here. What are we seeing in those lakes? Between 8 and 3 million years, we have fishes that say Lake Ringold was warm water and was isolated. Isolated from who? Isolated from the other lake. I'm no fish person. I know nothing about fish. I'll show you some pictures, but that's about it. But we'll take Jerry's word for it with the specialist that you can study fishes from this time and this time, same time, and there's no evidence of the fishes swimming between those two lakes. That's important to us tonight, isn't it? If you're not fishing, if you're not swimming between these two lakes, you got no river between the two lakes. But what happens at 3 million years ago? At 3 million years ago, between 3 and 2.8 million years ago, the same fish fossils are in both basins. And the fish thrive in cold water. And we have salmon now coming from the Pacific Ocean and getting into both of these places. In other words, we have warm fishes, separate warm fishes, no connection between the two, and then starting at 3 million years ago, we have the Snake River showing up, and not only showing up, but starting to dig to start our Hell's Canyon creation. So that kind of regional story can be told from these teeny tiny little fragments of little fishes, among other things. And that's where we've added Jerry Smith's work to some of this other stuff. Now, I promised the hotspot stuff and the supervolcano stuff. I got to do that real quick. And then I promise we're going to the visuals. Here's the last little part of this. If I pick 11.8 million years ago, who's got a good memory? Why is that date significant? The 11.8 million years ago from last week, that was the huge supervolcano explosion in southern Idaho. Does anybody remember it now? Right. It's right here. And ash from that Bruno Jar Bridge explosion 11.8 million years ago had 30 feet of ash fall out of the sky in central Washington. That was the Cougar Point Tuff that we discussed last week. Why in the world are we going to this now? The answer is, this is a cross-section now. This is a little picture here on the side. If you have Idaho, this is the sun. This is a person 11.8 million years ago. If you have Idaho sitting on top of a hot spot, that portion of Idaho is going to get heated up. It's a hot spot beneath that portion of Idaho. What's going to happen to that portion of Idaho? It's going to be heated up and it's going to be expanded. We're going to have thermal expansion of that section of Idaho. We're going to have a temporary dome where the hot spot is located. Why is that important to us tonight? Well, if you have a temporary high, a topographic high, aren't you going to have rivers draining away from that temporary high? So that fits right into our story, because when we had the Yellowstone hotspot located here, we had a continental divide. Just like we today have a caldera and a continental divide at Yellowstone Park. That means 11.8 million years ago, we had rivers draining to the Atlantic Ocean east of the continental divide, and some rivers, according to Jerry Smith's fish work, going down the Sacramento River to Central California. And we sure as hell didn't have the Snake River coming through Hell's Canyon. We're starting to form the lake at 8 million years ago. So let's do this. Let's jump to 8 million years ago. Now the hotspot is at Twin Falls. We've moved the continental divide a little bit. We still have our lakes going this way. We still have the Columbia doing this. But we're going to start forming a small Lake Idaho and a small Lake Ringold, and we're probably going to have some kind of little divide between those two lake basins. Let's jump ahead to 3. That's a magic number for us tonight, 3 million years ago. Now the hot spot is approaching Yellowstone Park. The continental divide has shifted again, and now our Lake Idaho has become very large. That's too large. It's become large. And Lake Ringold has become large as well. So at 3 million years ago, we begin the incision of Hell's Canyon. Is it simply getting Lake Idaho too big to finally fill and spill over this divide and start forming Hell's Canyon? Or is it more of a tectonic story to eventually get rid of these lakes and to get our Snake River story and to get Hell's Canyon to begin? You can see there's lots of things going on with this, and it's difficult to have one person to have a grasp on all these different areas, of all these different specializations. But we're getting closer to figuring that out. I don't want you to leave, and here's one way to do it. In the last 5 minutes of our visuals, we're going to have a brand new scientist show up on the scene, Lydia Steisch, and she has new evidence from the Ringold to suggest that maybe Hell's Canyon is older than 3 million years. Now, how could you leave after that kind of a teaser? Well, I think we need some visuals. I think we need some beautiful pictures, and I think we need a few maps that might help us a little bit. I think we need a little bit more fleshing out of some of those ideas. I know it went quickly. Thankfully, if you watch on YouTube, you've got a pause button. You can sit there and think about it for a while and then move on. But not here. I don't think there's a pause button on me or from your seats. So, Grand Canyon, how old? 6 million years old, saying the Colorado River started to dig that hole. Here's Grand Canyon from Google Maps. Here's Hell's Canyon from Google Maps. They look different, I'll grant you. I mean, beauty lies in the eye of the beholder. I don't know which one is more beautiful. That one's a national park, one of the 7 wonders of the world. And here's us in the Pacific Northwest. Orida. We did this on the chalkboard. There it is in living color. The age of the rock layers do not help us very specifically with the age of the canyons. More Google Maps from the south rim of the Grand Canyon. And on the Idaho side, an amazing place with alpine lakes up at the Seven Devils Mountains. Have you been up there? It's an amazingly alpine scene, and yet you can drop all the way down the 8,000 feet down to the river. So I joined a field trip 3 years ago with Basil Tinkoff from the University of Wisconsin. I learned an amazing amount about that area. And here's the old road that we took from Whitebird, Idaho. We were camping near there, Hammer Grade, I think it was called, and then followed this old dusty gravel road from the east and got ourselves down to Pittsburgh Landing. So here's at least one stretch of Hell's Canyon. You may know very much more about more stretches. This is the main stretch that I know from geology trips. I saw this in Lewiston, Idaho last month. It's an amazing place, and of course part of the allure is how remote and how few people there are out there. Now, if you're willing to jump to this area for just a second, thank you for doing that, number one. This is the Yakima River Canyon just south of Ellensburg, and for more than 100 years, people have been looking at Beavertail Bend, and I'm happy to say Beavertail Bend still exists. This is just this past winter. Jesse Peters captured this beautiful shot. We had a very tough February, if you weren't with us here in central Washington, but he was out on a cold night capturing this. And a more classic shot from Tom Foster, showing these amazing river meanders that have incised into the local basalt lava flows. What's the general message? Those flows used to be flat, they got folded, and as you fold those ridges, you form the canyon. And as I've been teaching for a long time now, it's the clockwise rotation of Northern California, Western Oregon, and Western Washington against the stationary Northern Washington and Canada that's responsible for the squeezing, uplift, and digging of the Yakima River to form the Yakima River Canyon. That's on a loop, obviously. But if we look at it more artistically, this is the Rosa area of the Yakima River Canyon. There's Burbank, and then Eaton's Ranch is up towards the top. Again, this is on a loop, and we can see that if the Yakima River Canyon is about 6 million years old, and it is, we've had this kind of gradual uplift, we think gradual uplift, over the last 6 million years for the Yakima River Canyon. But you heard one of my big points tonight. I don't see how that is the story at Hell's Canyon if we tie the uplift of Hell's Canyon and the uplift of the Wallowas and the Blue Mountains and the Seven Devils Mountains. I don't see how we can tie that to the clockwise rotation, mostly because of the location of Hell's Canyon being further east than most of that motion. I mean, these shots, amazing, by Hell's Canyon. This is the Grand Ronde River Canyon. You can see the same kind of amazing meanders that have incised. This is really tectonic geomorphology we're talking about tonight, trying to understand why rivers dig when they do. That's one aspect of it. And this is what I was trying to say with you all. Is there some sort of regional tectonic story involving uplift, involving some sort of change in the oceanic plates offshore that are most agree that the ocean plates are driving the clockwise rotation? So have we figured out the history of the Juan de Fuca plate and the Pacific plate at these two times in history to see if there's some sort of regional story that most of us are unaware of at the moment? I know this is very fuzzy, but Andy Miner, who's been a very helpful geologist with not only this lecture, but most that I've put together down here, he lives in Cle Elum. Andy sent me this. These are images, very sketchy images of sediments off the shore of Washington and Oregon. And the main thing to notice here is that there's a major unconformity. There's a major change between the folding of some of these older sediments and the layers that are above the red line are not folded at all. If you see this in geology, an unconformity represents some sort of tectonic event, some sort of uplift and erosion story. So even offshore, perhaps there's a record of this either 6 million or 3 million year change in the tectonic story. So this is the lecture that I did 2 years ago that I was talking about. And I'll summarize some of the main points from that. I focused on the Columbia River having this weird bend to it and wondered why it had a weird bend. And we decided in that lecture it was the great lavas that came out of these cracks that pushed the Columbia River west of Ellensburg for a time, pushed the Columbia River west of Goldendale for a time. And it's the lavas coming out of these deep fissures that's responsible for that. This is roughly 16 million years ago. You've seen this already. Floods of lava completely changing the river story and the topography of eastern Washington. And after most of those lava flows, we have this lifeless, featureless plain. If you get to the Grand Ronde River Canyon or other places where the rivers have dug more recently, you can see those layers stacked one on top of another. The German chocolate cake that's 3 miles thick in the middle of it near Tri-Cities. And the Columbia River has decided to leave where it was pushed, and at least south of Wenatchee, the Columbia River has decided to return to the central part of these great lavas. Why? Because the weight of those great lavas have depressed Washington, have depressed the crust below sea level. And water flows to the lowest spot. You heard it here first. Water flows downhill. Aren't you glad you came? So here's a map of where those great lavas are found. Here's the Snake River. This is a map of today, not in the past. Here's Ontario. You leave I-84 and Hell's Canyon up through near Riggins, etc., and the Salmon River coming in. So notice the Salmon River is coming into the Snake River today. And it's the Snake River that's coming up through southeastern Washington. Got it? That should look familiar to you. This is today. Well, let's go back a few million years. This is a familiar looking map in general, but notice this is the Salmon River 10 million years ago. And the Snake River is not in Washington at the time. And we know that was the Salmon River because of these river rocks, these red river rocks that came from the Seven Devils Mountains. This is the lecture a couple of years ago. I'm just reprising a few of these major points. So these beautiful spuds, these are actual river rocks, and these are potatoes from our kitchen. These actual river rocks are the size and shape of potatoes, and they tell a story of rivers changing their position. And if you have red river rocks, you have the old Salmon River coming into Washington at a particular time. This is up above Wallula Gap in Tri-Cities. The Salmon River coming through this area between 10 and 8 million years ago. Salmon River, you want more evidence that there was the salmon and not the snake, and therefore we don't have Hell's Canyon at this time? We have this famous place near Colotis where we have 3 different lava flows of 3 different ages that actually flowed down a river canyon, the Salmon River Canyon. So we have fossilized river valleys by lava flows filling those old valleys. The evidence is beautiful. And then, of course, there's the famous blonde quartzite river cobbles that tell the story of the old Columbia. If you find a bunch of blonde quartzites, you know that's the Columbia coming through your property at some time in the past, like this video clip. These are blonde, mostly blonde colored river rocks. In fact, some of these guys have been sitting next to each other for 8 million years until this morning. These are quartzites from the Rocky Mountains. The Columbia River brought these in. There can be no other way these rocks got here. So that was the emphasis of that lecture 2 years ago. The Columbia River, the Salmon River, and I purposely ignored the Snake and Hell's Canyon at the time because I didn't know any of that stuff. But I did have a few maps that I snuck in, and that's what caught the eye of the geologists that saw that lecture. And they said, hey, you've got the Snake River coming through this area during the time of the lava flows. I think you're missing the boat on that. You should talk to Jerry Smith about his fish fossils. And so that is kind of where I started this lecture about 1.5 years ago. What can I find out about the old Snake River system, Hell's Canyon, and Jerry Smith's work? So I taught a Geology 351 class last spring. Every Wednesday we went out from 1 o'clock until sunset. And we went to different places. And our theme for last spring was to go to as many places that had Ringold-like beds as possible to learn this story. So we started by going down to Granger where those big cobbles are located. And old Grandpa Carl here, Carl Hulbert, who's in the audience tonight from Granger, has been very generous with his time and his place to open it up for anybody who wants to come and learn about his place. His place is important. It's where the old clay pits are located. They used to have a brick factory down there. But it's the clay beds that were not my interest. It was the river cobbles. The river cobbles that helped tell the story of which river was here at which particular time. And the next few days, I came back with my Geology 351 students, and we said, well, we're just starting out. Why don't we head up here and take a look? I'm not even sure what we're looking at. I'm talking to my students now. Can we climb up there and make a few cross sections and try to figure out the variation in the rock layers here, which are sand and which are rivers. And I just assumed at the time it was the Ellensburg Formation that we were looking at. So you know that occasionally I post on Facebook, not my private stuff, but I like to use it for geology. And so I posted this after that trip that night, after I took the vans back to Motor Pool, sitting in the van, posting on Facebook, and said, hey, had a good afternoon with my students out at the Ellensburg Formation near Granger. And Bruce Bjornstad, a geologist in Tri-Cities, said, I don't think that's Ellensburg Formation. I think that's Ringold Formation. I don't know why you're calling it the Ellensburg Formation. And to most people, who cares? But to us, we do care, because if it's Ringold, the source of the Ringold sediment is coming from the Hells Canyon area, as opposed to calling it the Ellensburg Formation, which means those are things coming from the Cascades, which is a totally different story. So the Ringold Formation is all this sediment that sits on top of the basalts. That's why I never really cared about the Ringold before. I was interested in the basalt lavas. All that dirt sitting on top, I didn't care about. But now, if I realize that there's details in the Ringold that help us understand the Hells Canyon, then I'm all in. So where can we go find the Ringold? Well, we can go to this old town site of White Bluffs along the Columbia River. Here's a beautiful shot taken by Tom Foster. He's standing on top of Saddle Mountains looking south. So he's got the White Bluffs on the left, he's got Tri-Cities in the distance, and here are a couple of the reactors at Hanford on the right side of the photo. Now, there's Ice Age stuff out there at White Bluffs as well. Let's ignore that if we can, please. We just want to look at the Ringold portion of White Bluffs. And there's an amazing flat top to this pile of 1,000 feet of Ringold sedimentation, some of it below river level, actually. And suddenly we have respect for these layers, at least I do, because it's that Lake Ringold that we were talking about that's part of this Hells Canyon story. But not the Hells Canyon yet, right? If we have Lake Ringold and have these layers at the bottom of Lake Ringold, we are pre-Snake River, pre-Hells Canyon creation. What can we find in these layers of Ringold formation to help us with the development and the timing of Hells Canyon? Oh, a backpack. Oh, a van key and some interesting sedimentary structures. Again, I go to Facebook. I say, well, I take my students down to White Bluffs, and there's a guy from David Green from Wapato says, I used to collect fossils there at White Bluffs. And I'm like, you're kidding. What did you find? Where were you in the White Bluffs? Where in the Ringold, in other words? He said, I found camel, sloth, horse, beaver, squirrel, giant Irish elk, rhino, mastodon, antelope, badger. They were all disarticulated. There's a specific layer that produced all that vertebrate material. One layer in the 1,000 feet of Ringold. Well, I went down and visited with David at his home. He showed me all his wonderful fossils that he had collected before the Hanford site became protected. And this is a camel bone pulled right out of one particular layer in the Ringold. Here are some little vertebrae of something or other. I'm not much of a biologist, obviously. That turned me on to a report by a guy named Gustafson from University of Oregon, who looked at that vertebrate layer in the Ringold. And this is the cover of it, bulletin number 23, the vertebrate faunas of the Pliocene Ringold Formation. There's another mystery. If you're keeping track of mysteries, why are all these vertebrate fossils just in one horizon within this 1,000 feet of Ringold? And why are all the bones screwed up? Why don't we have intact carcasses? So by taking that report and Bjornstad's unpublished work from the Hanford site and Newcomb in 1958 and Lindsay in 1996, I made this generalized stratigraphic column of 1,000 feet of Ringold sitting on top of the Elephant Mountain basalt. And the main point for you is that there's hardly anything in the Ringold Formation to get a date from. It's very difficult to figure out where we are in time. So that's another major challenge. If we can find some key grains in the Ringold, which we're about to do with Lydia, we need to figure out when those grains were brought in. I'm a little ahead of myself, but I just wanted to keep us going here a little bit. Those red stars are the horizon where David and friends kept finding the fossils. So we brought a group of many of you guys out there last spring, And David was along. David's in the beard there, so he had a bunch of things to say to the group, and they really enjoyed that. It's always kind of fun after the trip. They said, I really enjoyed that fossil guy. Your stuff not so much, but that fossil guy I really enjoyed. And there's places you can get your hands dirty right there in the Ringold along the White Bluffs. Wonderful old mastodon, molars, etc. Of course it's interesting stuff. It's very different from our normal routine in geology. Well, here's a little bit on Jerry Smith, the specialist with the fish fossils. I've had emails back and forth, but basically his first email to me back last spring was, fish have some utility to be a fourth line of Paleo River evidence because of their tight restriction to water. And that has proven to be true, that his work, his long career with these fish fossils have really helped us. So digging through these papers with all this biology is very difficult for a guy like me, but I kept reading through, kept emailing him. He was very patient with me, and I got at least the gist of his story. It turns out one of the exposures of the Ringold that has been good for him was not at White Bluffs, but closer to Othello, on the north side of the Saddle Mountains. That's still Ringold there. So some of you may know, if we're up on top of the Saddle Mountains, it's Ringold Formation at the very top. It's the same stuff as the White Bluffs. The White Bluffs are up there in the upper right. Can you see them? So those white layers continue to the summit of the Saddle Mountains. But here's the Ringold again, right at Smyrna Bench, if you know Crab Creek there. There's a thick section of Ringold to study there. And there's some cows. And it's this spot that's been most helpful to the fish people, an exposure of the Ringold Formation at a spot called Taunton. And you're like, I've never heard of that. Well, that's where the Milwaukee Railroad was put through, just to the west of Othello. You might know it now. It's just south of 26. And that has been a very convenient place to sample for all these tiny fish fossils. Why would you do that again? What's the whole point? You're trying to figure out the Snake River's history and the source of the material in those lakes and the temperature of the water and whether there's a connection to the ocean or not. Well, let's take a look at some of these fish fossils. This will be fun. There's Grandpa Carl. Let's go check this out. Well, there you go. There's a fish fossil for you. I mean, look at the scale on these things. These are from Jerry Smith's scientific papers. That's a millimeter. So talk about painstaking work to sift through all this sand and silt and find these little broken pieces of different fishes and try to figure out the conditions in Lake Ringold and Lake Idaho and realize there's different species in both of those lakes between 8 and 3 million years ago. This is an amazing level of precision and detail that feeds into a regular regional story. Yeah, I know what that is. That's a fish head. Even in Nevada, there are some of these lake beds. So it's more than just a Snake River story. You can connect these old lake basins before there were through-going rivers through many of these intermontane areas. But here's the main point I was trying to drive home on the chalkboards. If it didn't work for you then, maybe it will work for you now. 1,000 feet of sediment in central Washington, 1,000 feet of sediment in southern Idaho, 2 different lakes, 2 different isolated lakes. This is a map from Lydia, who we'll talk about in just a second. No Snake River between them, no Hell's Canyon between them, and the evidence is we have fishes in this lake that are totally separate from different kinds of fishes in the other lake. Before 3 million years ago, the species, and I wish I could give you all the names, like sunfish and all these fishes that don't need cold water and don't need migration to the ocean, are thriving in those 2 separate lakes. But suddenly, between 3 million and 2.8 million years ago, things changed dramatically. The same fishes are in both beds. There's salmon coming from the ocean somehow, and the interpretation is it's the Snake River that's allowing that connection between these places. So it's time for some professional diagrams. 16 million years ago, we have a hot spot in northern Nevada. That red dashed line is the continental divide. We have green rivers flowing away from that continental divide. We've got the flood basalts coming out of those fissures. No Hell's Canyon, no Snake River. Moving on. 14 million. Why is the hot spot moving? Most of you know this. The hot spot is not moving. It's North America drifting to the southwest over the stationary hot spot. We still don't have our lakes. We still don't have the Snake River. But now we get these two, what look like hearts, Lake Ringold in darker orange and Lake Idaho in lighter orange with a little divide in between the two. Remember now, between 8 and 3 million years ago, those are isolated basins. We continued to drift the hot spot, which means we changed the drainage patterns, changed the rivers. I mean, it's 4 million years ago. We still don't have much that looks familiar, do we? I'm going to hit one more click of the advancer here. You ready? Oh, yeah. It happened that, quote unquote, quickly. 3 million years ago, we capture the whole scene, and then by the time we get to today, we've got the Snake River coming from Jackson Lake in Jackson Hole and the Yellowstone area. Okay, we're almost done, but I have to be complete with this lecture. Here's the new kid on the block. She replaced Ray Wells, who worked for the USGS for 35 years. She is good, she is smart, she is young, and she is turning this story on its head. And that's healthy if you are willing to accept all the new information coming in, which most of us do. So here's the main message from Lydia Stice, work she's done just in the last 2 years, and it's ongoing work. Lydia says, look, I've been studying the Ringold with my techniques, and I've got sand in the Ringold that's 8 million years ago from the Snake River Plain in southern Idaho. Now let's pause and just check this out before we quit. What is she saying? She says she has sand grains that are clearly, according to her work, we'll look at her evidence, from the Snake River Plain. And those sand grains were brought to central Washington and dropped into Lake Ringold 8 million years ago. Why are we pausing about that? Up until this point of the lecture, we've said that we don't have a Snake River coming through Hell's Canyon until 3 million years ago, right? This is the new exciting development that's stirring the pot a little bit. How is it possible, if those truly are grains of sand from the Snake River Plain, how did they get here? If not through Hell's Canyon, is there another option? So she got interested in the Ringold by accident. Her first major project, newly hired, was to work on the Saddle Mountains Fault. She's based in Menlo Park, down in San Francisco, but it was decided she was going to work on the Saddle Mountains Fault and figure out what kind of seismic risk we have here at Beverly. And she's working with layers that are exposed on both sides of the fault, the Ringold. So she did what she could to learn about the Ringold, primarily to say something meaningful about the Saddle Mountains Fault, which crops out right above the Smyrna Bench and has been a very active fault in the past. Still unclear how worried we should be about the future, but it's an active fault. And she published on that Saddle Mountains Fault and got that out there and feel like everything was fine. But then she said, well, wait a minute. I started finding all this interesting stuff in the Ringold. So I'm going to shift my focus, and that's where she is now. I want to learn more about this Ringold because I'm finding stuff that doesn't belong here. It's too old for the conventional story of 3 million years. So she now has presentations like this: Ringold Formation Sedimentology, Implications for the Ancestral Rivers of the Pacific Northwest, basically talking about Hell's Canyon development. So, turns out she came up to Ellensburg to give a talk right in the middle of when I was doing this 351 class. So that was convenient. And I said, well, I've been out looking at this stuff. What have you learned, Lydia? And she says, well, I've been sampling zircons, these little very durable grains that are in the sands of the Ringold, and she can get a lot of information out of those zircons. Details about not only the ages of the zircons, but the source of the zircons. Where did those sand grains come from? This is an exciting new technique that's been used. So you can find a certain zircon and trace it back to a particular watershed, someplace upriver where the sand grain was brought to. This is a powerful technique. Well, back to Grandpa Carl. I said, well, we got to go down and check out Grandpa Carl's place. He's got a bunch of sand that's in the Ringold. And I was all set to bring her up to all those river cobbles. I figured she'd want to deal with that. And she said, no, I got what I need right here. She pulled out a Ziploc bag and just grabbed a bunch of sand. It's the sand in the Ringold with the zircons in it that what is meaningful to her. And it's what's going to unlock this new story if it does become a new story in the next few years. Lydia had a summer field assistant. Forget what her name was. Sorry about that. She had another field assistant. Very cute dog that's with her at all times. She operates in style. This is her teardrop trailer that she camps in. So she's got a lot going on, and the Pacific Northwest is her domain. So we did climb up through Carl's layers, Grandpa Carl's layers. This is, again, Snipes Mountain, south of Granger. And there's beautiful old blocks of petrified wood that have been tumbled through there. That's a whole nother story. But later that day, Lydia gave a talk at Central. Some of you were there for that talk on her work with the Ringold Formation and using these zircons to try to figure out the source of the sand. Now, these are difficult things to read, but she basically has been sampling sand in modern rivers across the Pacific Northwest. Here's the Yakima River, Okanagan River, Matau, etc. And she's got a particular signature from those grains and where those grains are coming from, and then she compares it with the zircon signals in the Ringold and tries to compare Ringold sands with modern river sands and make a statistical case that many of the sands that she has in the lower Ringold are coming from the Snake River Plain. So she's making maps like this now with all these rivers, and here's our hotspot track and the supervolcanoes from last week. The Simcoe volcanics near Goldendale are part of this, but poorly understood, at least by me at the moment. And here's a map of where she has sampled in green. She's been collecting more sand from Oregon in 2018. Other spots of different colors she sampled at different locations. So this is an ongoing project, and potentially, all I'm trying to say here is that our crucial understanding of the age and development of Hell's Canyon may be changed from the 3 million year date if she continues with this work and makes it agreeable to all. These are the last two maps. Lydia currently has a couple of models. This is not her final decision, but a couple of working models. Let's look at this. Is it possible to get sand from southern Idaho to Othello, let's say, in Washington, without using Hell's Canyon? You see what she's doing here? She's wondering if it's possible to have a Salmon River route to get sand grains from the Snake River Plain, come up, this is my old thesis area, between the Beaver Heads and the Lemhi Range, and then continuing up into Lake Ringold. That's a potential. So it could be that the 3 million year date is accurate for Hell's Canyon if this is borne out with the data. Or, is it possible Hell's Canyon is much older than 3 million years? And we have our lake beds with limited circulation between the two lakes, but possibly can we get those sand grains to come through Hell's Canyon as early as 8 million years ago? If that's true, then Hell's Canyon is 8 million years ago at least, and we got a lot more time for the Snake River to dig, and a lot more time for uplift, and it's a whole nother spin on the whole thing. So the Snake River, and in fact all the rivers of the Pacific Northwest, are telling a story not only of canyon development, but regional uplift across the whole region. And I love this shot from Lynn Weisenfels near Hell's Canyon in the Grand Ronde scene with the Columbia River basalts and our familiar looking rocks with this deep level of cutting by many of the rivers in the Pacific Northwest. I want to thank you all, not only for coming tonight, but for coming to all four of these lectures this particular month of beautiful April here in Ellensburg, Washington. Hey, we'll see you next year, okay? Thanks, everybody. Thank you much.